Good morning. So today we are moving on to section 1.8. So let's go over this warm up based off of yesterday's lesson. So yesterday we talked a little bit about functions and making a function table. So here's our function, y equals 2x plus 3, and they are giving us the domain, which is 0, 3, 6, and 9. So the first thing we're going to do is put the domain into our input-output table in for the x values here. And then we can input each of those x values into our function rule and find those y values. So if I put in a 0, 2 times 0 is 0 plus 3. If I put in a 3, 2 times 3 is 6 plus 3 is 9. If I input a 6, 2 times 6 is 12 plus 3 is 15. If I input a 9, 2 times 9 is 18 plus 3 is 21. Now this would tell me that my range is 3, 9, 15, and 21. So now this time we're going to do the opposite. We're going to look at the input-output table and we're going to write a rule for this function. So we're going to look at that relationship. How are we getting from each of these x values to those corresponding y values? So when you're going from 0 to 1, there might be a couple different ways to do that, just depending on what's happening. Like let's say you're thinking, okay, it's plus 1, but then you go to the next one and you see 2 plus 1 is not 7. So in this sort of situation, I usually with zeros and ones, I would kind of skip that one, look at the other numbers, and then just make sure whatever you find for those works for that as well. So if I want to go from 2 to 7, I might add 5. That could be one option. But if I go to 4 and I add 5, I do not get 13. So it's not going to be 5, just x plus 5. So then you might think of some other things. Well, what if you multiplied the first number? Obviously, it's going to get bigger. So if you can't add something, maybe we can multiply something. So noticing that 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. None of those work out to 7, but maybe we could multiply it and then add or subtract something. So for example, if I did 2 times 2, for example, that would give me 4, and then I would have to add 3 to get to the 7. So if I try that over here, 4 times 2 is 8, but then if I add 3, I only get to 13. So that's not going to work. So maybe we try a different option. So maybe instead we try multiplying it by 3. So 2 times 3 is 6, and then I would have to add 1 to get to the 7. So now let's try it here. 4 times 3 is 12, plus 1 is 13. So far, so good. 9 times 3 is 27, plus 1 is 28. So it works for all three. Now I'm going to go back here. 3 times 0 is 0, plus 1 is 1. So that function rule works for those. So you can see that you had to kind of play around with it, do a little bit of guessing and checking. So sometimes that's what you're going to have to do to find that. All right, Jasmine sells bracelets. Her profit on each bracelet is $8. Write a rule that shows her total profit as a function of the number of bracelets that she sells. So normally when we see as a function of, we know that whatever comes before it is the y, and then whatever comes after it is going to be our x, right? So here they want us to use the variable p for profit as a function of the number of bracelets. It does say her profit on each bracelet is $8. So the number of bracelets she sells times 8 would give us that total profit. So this is what our function rule would look like. Now it says write the range of the function if the domain is those numbers there. So it might be helpful to put that into an input-output table. So I have my domain 5, 10, 15, 20, and 25. So if I was to sell 5 bracelets and I'm making $8 a piece, that would be $40 of profit. If I were to sell 10 bracelets at $8 a piece, that would be $80 of profit. 15 bracelets would be 120. 20 bracelets would be 160, and 25 bracelets would be 200. And so then you can see that our range is is simply 40, 80, 120, 160, and 200. All right, so we're going to move on now and talk a little bit more about our functions. So our objective for this lesson is to now represent these functions as graphs. So we did a lot with the tables yesterday, but we didn't actually graph them. So today we're going to get into graphing them and kind of see what do they look like. So let's say I were to graph this function here, y equals 3x, with the given domain of 0, 1, 2, 3, and 4. So typically the first step into graphing a function is to make an input-output table, because that's going to give us those corresponding x and y coordinates that we can plot. So my domain is my x values, 0, 1, 2, 3, and 4. And then as I input those values into my function rule, I'm going to get the y values that correspond. So 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and 3 times 4 is 12. So now each of these input-output pairings is going to be an ordered pair that we can plot on a graph. So if we look at this table here, this would look like these points, 0, 0, 1, 3, 2, 6, 3, 9, and 4, 12, and those are the points that we will plot onto the graph. So if we take a look at these, if I were to plot point 0, 0, that would be down here on my origin. Then 1, 3, so over 1 up 3, which is about halfway between those two lines there. Then 2, 6, 2, and then up 6, 3, 9, and then 4, 12. So you'll notice that this is a linear function because the points are all going in a straight line. Okay, so let's try these couple examples here. So first thing we will do is put that domain values into the input-output table. Then we are going to substitute each of these in for that x and find the range values or those outputs. Now you'll notice that the domain here is all even numbers, and that's nice because they're all going to get multiplied by this 1/2. And when you multiply 1/2 to an even number, you end up with a nice whole number. So half of 0 is still 0, and then we're going to add 3. Half of 2 is 1, and then we're going to add 3. Half of 4 is 2, and then we're going to add 3. Half of 6 is 3, and then we're going to add 3. Half of 8 is 4, and then we're going to add 3. Then I'm going to use these pairings as ordered pairs and plot them on my graph. So 0, 3, 2, 4, 4, 5, 6, 6, and 8, 7. And you can see once again, this is making a linear function. Okay, number 2. Again, we're going to plug the x in next to the 4 there. So our domain is given to us. It's just 1, 2, 3, 4, and 5. So each of those numbers will get multiplied by 4, and then we will subtract 4. So 4 times 1 is 4, minus 4 is 0. 2 times 4 is 8, minus 4 is 4. 3 times 4 is 12, minus 4 is 8. 4 times 4 is 16, minus 4 is 12. 5 times 4 is 20, minus 4 is 16. And oftentimes, once you start going through, you'll notice a pattern starting to emerge, and you can kind of fill in the rest of that input-output table. As long as your x values or the domain followed a specific pattern, you'll notice the pattern typically with your y values as well. 2 and 4, 3 and 8, 4 and 12, 5 and 16. Again, these are linear functions, which is why they are following those patterns, and they are graphing lines. All right, so let's try 2 more with some negatives here. That can sometimes make things a little bit trickier. So for this one here, our domain is 0, 4, 8, 12, and 16. We're going to be multiplying each of these by -3/4, which can become a little bit tricky. Now the 0 is no big deal because 0 times anything is 0, and then we're just adding the 6. But now we're going to put in a 4. Now notice if I'm doing -3/4 times 4, right? The nice thing about this is if you're doing multiples of 4 and that's the denominator, those will cancel. So you're just left with negative 3 plus 6, which of course is positive 3. Now when you try the 8, you're going to do negative 3/4 times 8. Again, those are going to cancel. The 4 and the 8 cancel, and that 8 reduces to 2. So you have a negative 6 plus 6, which is a 0. If I go to do the 12, negative 3/4 times 12, again, I can reduce this to a 1 and a 3. Negative 3 times 3 is negative 9, plus 6 would equal negative 3. Now at this point, you could probably start seeing this pattern emerge, that they're all decreasing by 3. So I could probably guess that my next one's going to be negative 6. If you want to check it, negative 3/4 times 16. The 4 and the 16 are going to reduce. Negative 3 times 4 is negative 12. Negative 12 plus 6 is that negative 6. Now I can graph these 0, 6, 4, 3, 8, 0, 12, negative 3, and 16, negative 6. Now you might have noticed that there wasn't exactly a 3 or a negative 3 on my y-axis. And I made that point kind of in the middle. It's like halfway between the 4 and the 2. And same thing down here. It's about halfway between the negative 2 and the negative 4. So sometimes that happens when you're graphing on a coordinate plane where every single number is not labeled. So don't let that throw you off or confuse you. All right, we're going to do one more here. So I'm putting in my domain that's given. It's just 1, 2, 3, 4, 5. You'll notice there's no fraction here, so it's just fine to just go up by numbers increasing order. We like to skip numbers when there's a fraction, because whenever you have a fraction, like you did in number 3 or in the previous one where we had the 1/2 up here, it's nice to use numbers that are going to be multiples of that denominator so that you don't end up with any decimals or fractions as your points, because plotting those is just more difficult. So that's why here we went up in multiples of 4, 4, 8, 12, 16, because they would all cancel with that 4 that was in the denominator. Just like the last problem, when you had the half, all the numbers were multiples of 2, 2, 4, 6, 8. And 0 is always fine to use no matter what, because it's just an easy number to work with. Okay, so negative 2 times 1 is negative 2 plus 7 gives me 5. Negative 2 times positive 2 is negative 4 plus 7 is 3. Negative 2 times positive 3 is negative 6 plus 7 would be 1. Negative 2 times 4 is negative 8 plus 7 would be negative 1. And negative 2 times 5 is negative 10 plus 7 would give you negative 3. Plotting these points here, I have 1 and 5, 2 and 3, 3 and 1, 4, negative 1, and 5, negative 3. And you can see it's another linear function. Okay, writing a function rule for a graph. So we did this with the tables yesterday or in the last lesson, but now we're going to do this with the graph, which is pretty much the same thing that we did, because you can just literally take the coordinates of each of those points and put them into a table and work with them that way. So this first point here is 0, 1. So that's why I'm putting that in my input-output table down here. This next point was 1, 3. Notice the dot's like halfway between the 2 and the 4. So that's why I'm saying that it's going up to 3. The next one here is 2, and I would say 5, because again, it's kind of halfway between the 4 and the 6. The next one will be 3, 7. And then the last one there would be, it looks like, let's see, 4 and 9. And this was 3 and 7. All right, now that we have our table, we can look at that relationship. So what's happening with the x's to get to the y's, right? And it doesn't matter which ones you want to look at, but I said to you earlier, going to 0 to 1 isn't really too helpful, so look at some of the other ones first. So what kind of equation here? What relationship is there between the outputs and the inputs? So what would I have to do to my x values to get my y? Well, to get from 4 to 9, I'm adding 5 To get from 3 to 7, I'm adding 4. To get from 2 to 5, I'm adding 3. So not the same number being added, but there is some kind of a pattern there. But let's talk about maybe multiplying something. Like if I multiplied 4 by 2, what would I get? 8, and then I could get 1, add 1 to get 9. What if I did 3 times 2? That would be 6, add 1 and get 7. 2 times 2 is 4, add 1 and get 5. 1 times 2 is 2, add 1. So I'm going to multiply them each by 2 and then add 1. So if just addition doesn't work, then try multiplying those x values by a number first and then adding if you need to, or maybe even subtracting. So that's our function rule. So now our domain was all those values in the x box, 0, 1, 2, 3, and 4. And then our range was all those y values that we got. And those were 1, 3, 5, 7, 9. All right, let's try another one. Writing a rule for this one. So first thing I'm going to do is pick up the points off the graph. So I have 1, 2. The next point is 2, 4. The next one is 3, 6. And the next one is 4, 8. And it looked like there was a 0, 0 too that I missed. So I'm just going to put that on the end because we probably would not look at that right away anyway. So now we need to kind of come up with what's that relationship. Well, I could do 1 plus 1 is 2, but 2 plus 1 is not 4. So I know this is going to be more than just an adding rule. So then usually what I go to is I start with multiplying those initial values by 2 and then seeing if that's enough, or do I need to tweak it by adding or subtracting. 2 times 1 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and of course 0 times 2 would be 0. So this is enough to be the function rule. We don't have to add or subtract anything to it, and that's it. So now we just have to identify our domain and range. Our domain would just be 1, 2, 3, 4, and don't forget that 0. Now notice I didn't put it in the beginning of my chart, but when we were listing the domain and range, they really should be in order from least to greatest. Like that. All right, let's try another one. All right, so this one is 0, and this looks like it's halfway between the 0 and the 1, so I'm going to say it's a 1/2. Then we have 1 and 1.5, or you could do point like 0.5 and 1.5 if you prefer. Then the next one will be 2 and 2.5, or 2.5 if you prefer decimals. Then 3 and 3.5, and then 4 and 4.5. So this one's pretty easy because each of these y values is simply just increasing by 1/2, or 0.5 if you prefer decimals. And then of course for these, I don't know if our domain is just 0, 1, 2, 3, and 4. And then our range would be 1/2, 1.5, 2.5, 3.5, and 4.5. And I believe that is it.